Let's say that an object starts its motion right here. I'll use an xi. Sometimes I use an x sub 0 for 0 seconds, and x represents its horizontal position. So that's its starting point. And it travels along over here. Let's say that that's 20 meters to the west. So it travels 20 meters to the west. Then they turn around and they go back 5 meters east. So they go back 5 meters east. All right. So this represents their final position. I'll put XF for final. That's an F. Try that one again. Okay. So what is their displacement? Well, their displacement is their final position minus their initial position. And what is this? Well, they ended up how far away from where they started? Well, they didn't end up 20 meters from where they started. They ended up 15 meters from where they started, and they ended up 15 meters to the west. That, whoops, I forgot to put my units in there. 15 meters to the west. That is a vector quantity. All right, the direction matters. I mean, what if they had continued? What if they had continued going back over here to where they started? Well, their displacement would be 0. That's not, they would have walked a total distance of 40 meters, right? 20 plus 20 is 40, but their displacement would be 0. What if they ended up over here, say 5 meters to the east of where they started? Well, their displacement would be 5 meters east. That's a vector quantity. It has magnitude, 15 meters. In this case, 15 meters. 15 meters to the west. So it has magnitude, 15 meters in direction west. Let's say that this whole episode took 10 seconds. So let's use a different color. So let's say that it took a time, delta t, of 10 seconds. Well, what's their average velocity? Well, their average velocity, which we represent v for velocity, a bar for an average, that is defined as displacement over time. And that would be 15 meters all over 10, which equals 1.5 meters per second. And that would be to the west. That is a very simple vector problem. You express them with magnitude and direction. Now, what happens if you have magnitudes that are, if you have vectors that are in the same direction, but you have more than one vector? Let's change this completely. Let's just say that you are paddling in your boat, you know how great an artist I am. So here's the ocean, and you're paddling with as much force as you possibly can. And when you paddle with as much force as you possibly can, let's put that green because this is you are paddling at, say, 3 meters per second to the west. But let's just say there's a current. So the ocean, there's an ocean current. Or maybe you're paddling downstream. Beats the heck out of paddling upstream. So let's say that the current is 2 meters per second west. Well, notice that these two vectors are in the same direction. So what is the resultant velocity? So how fast are you going compared to, say, somebody standing still on the shore? So your resultant velocity is the sum of these two. So you would add up 3 meters per second west plus 2 meters per second west would be 5 meters per second to the west. All right, so that's your resultant velocity. But what if you're paddling against the current? So here you are in your wonderful little boat. Here's the ocean. This is a nice pale color because you're in Hawaii. That would be nice, wouldn't it? And that current is still 2 meters per second to the west. And you are still, being as buff as you are still paddling 3 meters per second. By the way, I should have made that arrow longer up front here. Let me tell you why. And I'm going to make this one longer too. Because 3 is bigger than 2. And the arrow should be drawn longer because it represents the number 3 versus the number 2. And the size and the direction of the arrows represent the size and the direction of the vectors. All right? 3 versus 2, and they're both west. That way. Okay, in this case, of course, you've got 2, and this is going to be 3. So this would be 3 meters per second east. Now, here you have to make a judgment call. One of these directions, because they're opposite directions, to west and east, one of them has to be made negative. Which direction you make negative is totally up to you. I am going to make east negative. Why? Because I feel like it. So what, according to somebody on shore, what is your velocity? That's what we want to figure out next. So you just have to just write this as an equation. That would be 2 meters per second west plus a negative or minus 3 meters per second east. And so your resultant velocity is negative 1 meter per second. Or you can write that as that, or you could just write it as 1 meter per second to the east. All right? So relative to the shore, you're going up rather slowly upstream. That's what that represents. I want you to notice before I end this segment that we were able to add the vectors up here because they're in the same direction. We're able to subtract these vectors because they're in opposite directions, but in both cases, they're in the same axis. They're both in the x-axis. What I mean by that is they're both left or right. Same axis is left or right. If one of these things had been like up and down, or maybe perpendicular, or to some other direction other than just straight back and forth, we could not have done this so simply. We'd have to use some trigonometry. And that's where we're going next.